Hello everyone, today I will be discussing the Raman effect, that is the nature of the Raman effect. What happens that when a strong beam of visible or ultraviolet light interacts with a molecule gaseous state or the liquid or the transparent thin film, and the light is scattering in all the directions, and once you are measuring at the output this is scattered light, then the most of the light you are getting that having the same frequency, and these lines are called the Rayleigh lines. On the other hand, and a very weaker and another two lines you are getting, the both side of this lesser frequency or the lesser wave number with respect to this exciting line, and the higher frequency or the higher wave number of the exciting frequency. So now once you suppose this is my exciting line, and this is called my Rayleigh line, and here also we are getting that two lines, these are separated with a delta nu. Higher wavelength side, higher wave number side, and a lower wave number side. And these are called the Stokes lines, and these are the anti-Stokes lines, and which are separated with an equal distance. What it was observed that if, and this is being a constant, if exciting source remaining if I'm changing the exciting source, and if the substance is not changed, then delta nu is constant. Whatever either I'm changing this exciting line, corresponding to that for the molecule, I'm getting the same delta nu. However, if I'm keeping that exciting source, exciting line, that is what I'm calling that the visible or the ultraviolet exciting source, then if I'm keeping it as a constant, then if I'm changing the substance, then the delta nu is changing. And if I'm changing this one, but molecule or the substance scatterer is not changing, then delta nu is constant. So what it reflects that, what it depicts that, it is providing a complete the characteristics of the molecule or the characteristics of the substance. And now with this observation, we have two very strong observations with these measurements. If I have a low resolution spectrograph, if I'm collecting the scatterer's light, if I have a low resolution, you have three lines. This is Stokes, Rayleigh line, and the anti-Stokes line. So what happens that this delta nu is, both the side is constant with respect to this exciting line, and this is called the Raman displacement delta nu, and this agrees, this delta nu agrees exactly with the wave number of the main vibrational rotational absorption band in the near infrared spectrum of the molecule. If in a near infrared spectrum, if I'm observing the pure rotational vibrational absorption of the molecule, then this is the same quantity. And this is found to be the case for all these diatomic molecules for which both the Raman spectra and the infrared spectra are observed. Now, number 2, under a high resolution, the exciting line is found to have both sides close approximately equidistant lines. This is pure rotational spectrum. Now, if I'm going for the higher resolutions, then you are getting that lines over here. Here as well you are getting the band kind of the. So under the high resolution spectrograph, once you are looking at either side of this Rayleigh line, you have these lines as well, equally spaced, and these are spacing is just all approximately twice of the far infrared observations, and these are showing that they complete the rotational spectrum. And the separation between successive rotational lines is very nearly twice of the separation between the successive line in the far infrared spectrum of the molecule. The Stokes and anti-Stokes line referred are also found to be comprised with a rotational fine structure, and these are also defined as a rotational fine structure, and it is a completely strictly the rotational vibrational spectra they are showing that. So this is the Raman effect. This delta nu that is, it is showing that the far infrared spectra of a pure vibrational rotational of the vibrational rotation of the molecule, and these are showing that the purely rotational spectra, and either side of this exciting relay lines, and the spacing is just twice as compared to the far infrared spectra. So these are the observations for the Raman effect of the Raman spectra. Now I am not going to much detail of its experimental setup, how we can achieve these spectral lines or the Raman spectra. It is simply that this strong visible or ultraviolet light is interacting with my molecule or the gaseous state or the liquid state or the transparent thin film, and this scattered light is collected with the help of the spectrograph with the fine arrangement of these slits. Then you are defining these spectra. So the experimental setup, I am not going much into detail. So directly I am discussing about the classical theory of Raman effect. What classically we can, and how it is the classical theory is failed to explain this Raman effect. Then we will jump to the quantum mechanical approximation, quantum mechanical theory of the Raman effect. So the classical theory of Raman effect. So this is just now classical theory, that is atomic polarizability. Based on this atomic polarizability, we'll be explaining that how this Raman effect took place. So the elementary idea of this Raman effect can be explained with the help of the classical theory. When a beam of visible or the ultraviolet light interacts or falls on a molecule, the rapidly oscillating electric field of the beam induces an oscillating electric dipole moment in a molecule, irrespective of whether the molecule has a permanent dipole moment or not. Simply, once you have a strong electric field, what I am saying, that the intense light, so then you have a molecule, the nucleus, you have a positive charge, and here is a negative charge. So once you have a strong electric field, then what will happen that the shape of this, slightly the positive charge will be shifting in this side and the negative charge is this side. So it is inducing that the dipole moment of the molecule. So once the dipole moment is induced, then it is also oscillating with the frequency of incident light. Then if the dipole is oscillating, then it is radiating the energy. So now what we are presuming that, suppose, and then once this induced charge is induced, that dipole moment is induced, that is, then the material is polarized now. So suppose the field associated with the light beam of the frequency nu naught. Suppose a field, that is the intense field, that is coming with the frequency of nu prime, then this E is equal to, I could write this E naught of sine 2 pi of nu prime of t. This is my field. These are the vectors. Equation number 1. And it induces the dipole moment. If it induces the dipole moment of P is equal to, we know that is alpha of this E, where E is equal to E naught of sine 2 pi of nu prime of t, where alpha is called the polarizability of the matter, is polarizability of the molecule. So now this molecule behaves like a horizontal oscillator, and it radiates the energy from an electromagnetic wave of a frequency nu prime. This is called the Rayleigh scattering. Now, because this dipole moment induced, then the alpha is a polarity, and now it oscillates with the same frequency, and it radiates the electromagnetic wave with the same frequency, and these are called the Rayleigh lines or the Rayleigh scattering. Now the molecule has Now we know that this molecule has its internal vibrations and the rotations as well. So what happens that now we know that this diatomic molecule, it having its vibrations and the rotations as well. Now once it having this vibration and the rotations as well, as the strong electric field is incident on these molecules, such molecules, they induce a permanent dipole moment. So, corresponding to their vibrations and the rotations, the polarity also changing. So, it means that suppose I have alpha is a polarity, then this alpha of oscillation of with the vibration nu plus of alpha 1 of nu sine 2 pi of mu oscillating of t. Equation number 3. So the vibrational variation in a polarity may be written in this form, that alpha is equal to alpha naught of nu plus alpha 1 nu sine 2 pi nu oscillating of t, where this alpha naught of nu is your value of alpha, that is the once these atoms are at an equilibrium distance, whereas this alpha 1 of nu is the maximum change in alpha during the variation. So this is the maximum change of the variation in the alpha when you have this vibrational frequency is nu oscillating. And similarly for the rotational one, once you have a rotational frequency, certain rotational frequency, again it with respect to this rotation, there must be a variation in the polarizability. Then this alpha is equal to alpha naught of rotation plus alpha 1 of rotation and sine 2 pi of 2 of nu rotation of t, equation number of 4, where alpha naught r is the average value of alpha and alpha 1 r is the maximum change in alpha during the rotation. The frequency with which the polarizability changing during the rotation is twice of the rotational frequency. Now here if you remember, you just notice that here I am putting this 2 of nu t, because in a one rotation, if you look at, if you have a molecule is rotating, this is rotating, so this is plus of minus suppose, then the next one, then it is the minus of plus, and again to coming its initial place, this is plus of minus. So what happens that in a one complete rotation, it is changing this polarizability 2 times, because in an opposite direction, in a linearly in an opposite direction, polarizability remaining the same. It means that if in a one rotation, this is changing the polarizability twice. So that is why we are putting this 2 new rotation of t. It is a very important point at this. Since the polarity in the same along the opposite direction of the molecule. So now we need to write the induced dipole moment in a vibrating molecule. Now once the first case, once I am considering that the vibration, then this polarity P of nu is equal to alpha of this E. So I have this alpha of E. E is I have this E naught sine 2 pi nu prime of t from equation number 3. And just to put the value of alpha, this alpha naught of nu plus alpha 1 of nu sine 2 pi of nu oscillation of t, and this E naught sine 2 pi of nu prime of t is equal to just this alpha naught of nu E naught sine 2 pi nu prime of t plus alpha 1 of nu E naught sine 2 pi nu oscillation of t and sine 2 pi nu prime of t. And simply here you have a sine A and sine B. Sine A and sine B. So simply I could write this expression, this alpha naught of nu E naught sine 2 pi of nu prime plus alpha 1 of nu, and this E naught divided by 2, and sine A plus of sine B, I could write simply this cos 2 pi of nu naught nu naught nu naught of V oscillation of t minus cos 2 pi nu prime plus of nu oscillation of t, because we know that this sine 2 sine A of sine B is equal to cos A minus B minus cos A plus of B. And similarly we could write for the case once we have rotational molecule, this PR is equal to this alpha of this E is equal to alpha of E naught sine 2 pi of nu prime of t. In place of this alpha you have this alpha of 0 rotation, not rotation, plus of alpha 1 rotation of sine 2 pi of 2 nu rotational of t and this E naught sine 2 pi of nu prime of t. And similarly, in the same fashion that you can use that relation, then you have this alpha naught r of rotation, this E naught sine 2 pi nu prime of t plus this alpha 1 r of nu naught divided by 2, and again you are using that is sine A plus and sine A and sine B, and simply you have this cos 2 pi of nu prime minus 2 nu rotational of t minus cos 2 pi nu prime plus of 2 nu rotational of t. So if you look at, we have nu prime frequency in our output, nu prime minus 2 nu rotational frequency, and a nu prime plus of 2 nu rotational. In the same fashion that in an earlier relation that P of, that's the dipole moment, induced dipole moment P nu is equal to, we have got this nu prime frequency, nu prime minus of this nu vibrational, and a nu prime plus of nu vibrational. So this is the mathematical, how the classically we can explain. So the induced dipole moment changes not only with the frequency nu prime, also with respect to the incident light, but also with the frequency. Now what we have the frequencies at the output. Now we have nu prime frequency, nu prime plus of nu vibrational, that is the oscillation, and nu prime minus of nu oscillation, and this nu prime plus of 2 of nu rotational, and this nu prime plus minus of 2 of new rotational. These frequencies we are getting in the output. So, hence the spectrum of the scattered light are obtained by Bristol Raman lines at a distance, vibrational lines at distance, new oscillation on the either side of the Rayleigh line. So, in the either side of the Rayleigh line, we are getting these frequencies. Also obtain the Raman lines at a distance of the -2 new rotational and +2 new rotational. We are getting the rotational lines, and it is clear that the molecule need not to have a permanent dipole moment for its infrared spectrum to appear. So if you remember, once we deal that the rotational and the vibrational spectra, there is a primary condition that the molecule must have the permanent dipole moment. However, in this case, it is not required to have a permanent dipole moment to achieve that these Raman spectra. So it means that besides the molecule like the heteronucleus, so the homonucleus molecules like N2, S2, O2 also show the Raman spectra, although they do not show the infrared spectra. So there are two disappointments from the classical theory. Now I'm writing that these are the classical explanation. There are two disappointments from the classical theory. Number one, according to the classical theory, the Raman lines on the two sides of the Rayleigh lines must be the same intensity. Actually, the Raman lines on the high frequency side, anti-Stokes, are too weak to be observed. So if you remember, the anti-Stokes lines are the weaker. Classically, they must be having the same intensity, but in the observation it was not measured. Number two, another disappointment from the classical theory. While V oscillating has a fixed value, this new oscillating is a fixed value now, because you have the characteristics of the molecule. So this new rotational can take any value. Therefore, classically the rotational Raman spectra must be the continuous on the either side of the undisplaced line. This is the contrary of the observation. So what it means that it is a fixed value. Then either side of the rotation, either side of this unscattered light, there must be a continuous spectrum of the rotational line, which is the contrary of the classical theory. And this is all about the classical theory, then how it is felt that classically all these Stokes line and the anti-Stokes line, Stokes line and anti-Stokes lines must have the same intensity, but it is not observed. On the other hand, in the second disappointment that, but this is the V new oscillation is fixed, then either side of this Rayleigh line, unscattered line, there must be a continuous spectrum or the continuous spectra of the rotational spectra, which is not, it is a contrary of the observations. Then we will explain this quantum mechanically how this Raman effect is applicable, why it is then anti-Stokes lines are the weaker, why these lines are the stronger. So for today class, and I will be stopping at this point, then we will discuss the quantum mechanical explanation of the Raman effect. Thank you.